So question 13 on the VCAA 2019 chemistry exam is this. And I've already started it here because I had someone come in before, but anyway. Which of the following statements is about flashpoints is correct? Well, what is a flashpoint? A flashpoint is the lowest temperature something will be when we have enough vapor to burn. So we're looking at the temperature that something can actually ignite at. So the flashpoint of butane is lower than 25 degrees Celsius. I've put a tick next to that one because I know butane is a gas, and then this here is room temperature. So I know butane will burn at a lower temperature than 25 degrees Celsius because I know butane will burn at 25 degrees Celsius easily. Even a cold can of butane will still combust. All right, so therefore I know that that's going to be correct. I'm just going to try and eliminate these other ones here. So as a flashpoint increases, viscosity decreases. That doesn't make sense to me because viscosity is how, viscosity is the resistance to flow. So about how thick a compound is. So therefore, if you are decreasing its viscosity, you're making it less thick, so it's more runnier. So therefore, what that means is it will be more likely to form into a gas. So therefore, the intermolecular forces are lower, which means that the flashpoint will also be lower. So as viscosity decreases, flashpoint should also decrease because there's more likely to be vapor around to combust. The flashpoint of a compound is higher than its boiling point. Well, I know for a fact that ethanol can burn at room temperature, and ethanol is a liquid at room temperature. So therefore, the flashpoint for ethanol must be lower than its boiling point because you can burn a liquid. The flashpoint of butane is greater than the flashpoint of butanol. Well, this comes down to, again, flashpoint related to intermolecular forces. And the stronger the intermolecular forces, the higher the flashpoint because the harder it is to form a vapor. So butane is going to have dispersion forces, whereas butanol is going to have hydrogen bonds. So therefore, that's not going to be right as well. It's going to be A, because butane is definitely going to have a lower flashpoint than 25 degrees Celsius because I know it burns at room temperature. Question 14. This is a diagram of a non-essential vitamin. I don't know what vitamin it is, but it's a non-essential one. What that means is it is produced by the body and we don't need to ingest it with our diet. Looking at the structure of this, again, I've got this situation here. This here means we've got 10 carbon groups or chain, 10 of these long. So it's actually not just 10 carbons long, it's 1, 2, 3, 4. So 1, 2, 3, 4 times 10 long. So therefore it's going to be about 30 carbons long here. So it's massively non-polar is what I'm trying to get at anyway. So that means this is going to be a fat-soluble vitamin. Now that's what the question is actually asking us. This vitamin is fat-soluble and can be produced by the human body. It's not essential, so therefore it can, so that's good, and that's good. Cannot means not right, not right. So therefore it's fat-soluble, so that's the answer there for A. So the idea is that fat-soluble because it's non-polar. We do have a little bit of oxygen action over here, but in comparison to how much non-polar long hydrophobic chain we have, this is mostly going to be non-polar, so it's fat-soluble. Moving on to question 15. Aspartame has only one chiral center. All right, I need to get the structure of aspartame from my data booklet. Let's just find that first of all. It's somewhere here. All right, page 9 has my structure of aspartame. So let's look for chiral centers first of all. So this is not chiral because I've got a double bond to oxygen. This is not chiral because it's got 2 hydrogens coming off it. Chiral centers, you need to have 4 different things coming off the one carbon. This carbon here, we've got a nitrogen and a hydrogen that you can't see, and this, so therefore this is a chiral center right here. So that's one chiral center. That's not chiral because it's got double bond to oxygen. That's not even carbon. This carbon here, I've got a nitrogen, a carbon bonded to oxygen. This is another chiral center here because I've got 4 different things coming off it. Remember, this is a skeletal structure, so there's going to be a hydrogen coming off this. There's a hydrogen coming off that. This carbon here has got 2 missing hydrogens, so therefore it's not going to be chiral. This is a carbon from a benzene. None of these are going to be chiral because benzene rings are not chiral, and that means it's got 2 chiral centers. So what that means is it's not one chiral center. 2 stereoisomers. Well, stereoisomers are about double bonds, so therefore it's not going to be that because there are no carbon-to-carbon double bonds here. Even in the benzene here, that's not really a carbon-to-carbon double bond. It's actually like if we put a ring there, it would make more sense because each of these carbons is equal. They're not really double bonds as such. They don't behave like double bonds in a benzene. 4 optical isomers. Now, optical isomers come from chiral carbons, so therefore each chiral carbon will produce 2 optical isomers. So what we have here is we've got 2 chiral carbons, so therefore we're going to have 4 optical isomers. So that's going to make sense for C, because we're going to have, obviously, we're going to have this chiral carbon, so you can have 2 options from here. For each of these 2 options, you're going to have 2 options here, so therefore you're going to have 4 in total. 3 structural isomers, not right. Structural isomers come from different arrangement of the atoms in your molecule, and we've got a whole bunch of atoms here, so numerous different structural isomers would be formed, so therefore it's not going to be that one. Answer is going to be C, 4 optical isomers, because of the 2 chiral carbons. If you have 1 chiral carbon, 2 optical isomers, 2 chiral carbons, 4 optical isomers. Let's move on to question 16. So question 16, the number of carbon-to-carbon double bonds in a molecule has been identified by reacting the molecule with hydrogen gas. The type of reaction involved is an addition reaction. We know that anyway, because carbon-to-carbon double bonds, addition reactions, they go hand in hand. We've got 10 grams of fatty acid fully saturated after reacting with hydrogen. So therefore, what we need to look at is the ratio of fatty acid to hydrogen. What is the ratio that is happening here, and does it marry up with how many double bonds there are? First things first, I'm going to look at these fatty acids and work out if there's anything I can rule out because they are saturated. So where are my fatty acids? They are in my data booklet on page number 7, so therefore they are here. So let's have a look. I've got oleic acid. It is here. It's got 1 double bond, so the ratio should be 1 to 1 if it's going to be oleic acid. Linoleic acid is here. It's got 3 double bonds. Okay, arachidic acid, however you say that, it's got no double bonds. It can't be that one at all, because if it was that one, I wouldn't react hydrogen with it at all. Next up is this guy here. He has got 3 double bonds from here and another double bond there, which makes him have 4 double bonds. So what we want to look at is what our ratio of fatty acid to hydrogen is and work out which ratio is correct. So open this up and I work out how many moles of hydrogen I've got. That's going to be equal to 0.263 divided by 2, because it's mass over molar mass. And that's going to be 0.1315 mole. Don't even need my calculator for it because it's just halving it. But I do need to work out this. So oleic acid, if I want to work out my number of moles of oleic acid, I'm going to take my 10 grams, I'm going to divide it by the molar mass, which is 282, equals that. And it would be a 1-to-1 ratio, and it's not. You can see that the number of moles of this reacting would only be 0.035. So therefore, that's not going to work for us. Let's look at my next one and look at linoleic acid. 278 divided by, 10 divided by 278 equals, that's my number of moles of fatty acid. I have 3 double bonds, so times that by 3, that would be how much hydrogen I should need, and I don't actually have, I'm reacting more hydrogen with it. So it's not 3 double bonds there. All right, clear. This one, I've got 10 divided by 304 equals that many moles of fatty acid. 4 double bonds in that, so times that by 4, I've got that much hydrogen actually reacted, so therefore it has to be D. All right, simply by going through and working out if I was this one, how much hydrogen would I need? And we can go through that part there. But it's definitely going to be D because of that ratio happening. Question 17. The traditional bonding baby shoe, blah, 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 during electroplating process. So looking at this, it's an electroplating process. What am I plating? I'm plating baby shoes. That's pretty cool. Anyway, the copper electrode is oxidized and its mass is unchanged. That's not true. The copper electrode, if you're electroplating something, this will be your cathode because you want reduction to occur, and therefore this is going to be oxidized. All right, so the copper electrode will actually undergo oxidation and it will corrode, and therefore the mass will actually decrease in that particular electrode. The shoe is coated with copper metal at the cathode. That is definitely true by default. By electroplating, you connect what you want to plate to the cathode because you want reduction to occur there. So B is definitely the right answer. Just go through it. The copper electrode is the oxidizing agent. No, it is undergoing oxidation. It is actually the reductant that is the copper electrode, and oxygen is produced. It's not right, because you know in electroplating you have to produce a metal, because, well, if you don't, you're not electroplating. So that's not right. So B is the right answer for question 17. Question 18. And I've got a whole bunch of different galvanic cells. I can tell they're galvanic cells because they're separated and I've got a salt bridge happening. So it's just the difference between electrolytic cells, where they're all together and you have a power supply, and you have galvanic cells where you don't have a power supply and you've got a salt bridge. Anyway, which of the following galvanic cells will produce the largest voltage under standard laboratory conditions? So I go to my trusty electrochemical series and I work out what the difference will be for each one. So first up, we're looking at zinc and nickel. So I find zinc and nickel here. Here's nickel here. Here's zinc here. The difference between these two is going to be 0.51 volts. The next one, so this is going to be 0.51 volts. Difference between iron and hydrochloric acid. Well, hydrochloric acid is going to be my standard cell here, and iron is this one here. So therefore, what's the difference in this one? Difference between this and this is going to be 0.44 volts. In cell C, I've got silver and copper. So where's silver and copper? Silver and copper on my electrochemical series is here and here. And I've got a difference between that and that, which is going to be 0.46 volts. So that's going to be 0.46 volts. And lastly, I've got tin 2 and tin and pure water. Well, pure water is here. Tin 2 is here and tin 2 is here. I'm not actually going to get a reaction there at all. So therefore, the answer has to be A, because that has to be the largest at 0.51 volts in that galvanic cell. Just by simply taking this, looking at electrochemical series, working out your voltages, and then annotating as we go along. Question 19 is here. Question 19, lactose is commonly found. So it's about lactose, probably about lactose intolerance, and it is. So lactose intolerance describes the limited ability of humans to hydrolyze lactose. Consider the following statements. Statement number 1, lactose intolerant people produce too much lactase. That is incorrect. Lactose intolerant people don't produce enough, meaning that they can't actually break down lactose. So therefore, insufficient lactose leads to some lactose not undergoing hydrolysis in the human body. That makes sense. All right, because that's what lactose intolerance actually means. Lactose intolerant people can add lactase drops to milk to help digestion. That's true. All right, we can actually do that, because if you add your lactase, you're going to start digesting the milk before you actually drink it, so it's actually not too bad. Lactase assists in the hydrolysis of lactose into 2 glucose molecules. That is incorrect, because lactose is not 2 glucose molecules. It's actually a glucose and a galactose. And that's something you should be aware of from your studies in food chemistry. So therefore, 2 and 3 are correct. So the answer here is going to be C. Question 20. The oxidation of sulfur dioxide to sulfur trioxide is here. An equilibrium mixture had this much, that much, temperatures that. What is the equilibrium concentration of that? So I need to do equilibrium constants equals products squared over reactants O2 SO2 squared, and that is going to be equal to, well, I've got a KC 1.75. Let's bang in the concentrations for the other things. I'll work out what I need to know. I need to know that, so that's going to be x squared divided by my concentration of oxygen, which is 0.16, times my concentration of sulfur dioxide, which is 0.12 squared. So therefore 1.7 times by 0.16 times by 0.12 squared equals x squared. So square root all that. Let's go through my calculator and work out how I'm going to do that. On clear 1.75, 1.75, it says 75 there, times by 0.16 times by bracket 0.12 bracket squared equals that, and I need to get the square root of that, so therefore where's my square root on this button? Second function, that one, my second function answer. See how I'm using my answer button? That's kind of good to know, and that's going to be equals 0.0635. So therefore, answer is closest to D, because this is obviously 6.35 times 10 to the power of negative 2. I'm going with 6.3 is good enough, because technically if I did just two significant figures, I would be rounding down to 6.3. And that's good. That's question 20 out of the way. Question 21. The diagram below shows the Maxwell-Boltzmann distribution for an uncatalyzed reaction. So I love these ones. This is about rates of reaction clearly. So what's going to happen here is if I add a catalyst, what's going to happen to my curve? So adding a catalyst is simply going to change where EA is. So EA is now going to be here with a catalyst. Okay, so the curve flattens to reflect a lower activation energy. That is not true. The curve's going to stay where it is because this curve represents how much energy particles actually have. By adding a catalyst, we haven't changed the energy of the particles. We've simply just moved activation energy lower via an alternative pathway. So that's not right. Question 2, the curve shifts to the right. Not true as well, because we're not changing the we're not changing the energy of the particles. Question 3, EA shifts to the left. That is true, so therefore it's D, 3 only. And again, let's summarize that. A Maxwell-Boltzmann distribution shows you how much energies particles have. By changing or adding a catalyst, you do not change how much energy particles have, but you do lower the activation energy. And hopefully that makes sense to you. Question 22. Which of the following statements about conducting an experiment is the most correct? Precise results may be biased. That's true, all right? Because bias doesn't come from precision, so therefore bias could come from anywhere else. Let's go on the next one. Accuracy is assured if sensitive instruments are used. This idea of assured, well, you're going to get probably precise things, but they might not be accurate. So it's not assured. You can't really assure accuracy just by using sensitive instruments. I mean, your method might be completely bonkers, but you are still using sensitive instruments. It's not going to get accurate. All right? You probably get precision, but you're not going to get accuracy. A method is valid if it identifies all controlled variables. That sounds okay, but I'm not 100% sure on that one. Repeating a procedure will remove the uncertainty of results. That's not exactly right. It's probably going to make it more reliable if those results are the same. However, it's not going to remove the uncertainty. If anything, repeating a procedure is going to make it more uncertain because you have more spread of results. But I don't know, but definitely not that one, because repeating is all about reliability. And this is not to do with reliability, this is uncertainty. All right? And you could repeat it. If you get similar results, you have less uncertainty about your thing. But yeah, it's not going to do that. Precise results may be biased. I think that's the most correct, because a valid method identifies, I think identifying the controlled variables, you must actually ensure that they are controlled. So I'm going to say A for that one, but it's really between A and C. It's almost a 75-25% stab in the dark, but that one makes more sense to me. Question 23. Which of the following statements about enthalpy is correct? Enthalpy is about the idea of energy. So what's going to happen to enthalpy? And it's energy like delta H style. So this is delta H. Right, energy released within a chemical reaction. The sign of the enthalpy change in an endothermic reaction is negative. That is completely wrong. The sign of an enthalpy change for a condensation of gas to liquid is negative. All right, so let's have a look at it. Gas to liquid would be an exothermic reaction. Is that true? No, I don't think so. I'm going to move on anyway. Let's have a look at the other ones. So then I'll come back to that one if I don't see it. The enthalpy change is different between the activation energy, the difference between the activation energy and the energy of the reactants. No, it's the difference between the reactants and the products. The enthalpy change is the difference between the activation energy and the energy of the products. Not true either, because the enthalpy change is the difference between the reactants and the products. Activation energy has really nothing to do with it at all. So B is actually looking like our right one. So let's have a look, let's tease this out in our heads. What's happening when we go from a gas to a liquid? When we go from a gas to a liquid, we are cooling something down. Are we taking energy in? We're giving energy out. We're giving energy out because it's negative. All right, let's go the other way. Let's go from liquid to a gas. All right, if I have to go from a liquid to a gas, that means I have to provide energy to it. So it's going to absorb energy. So that means liquid to a gas is going to be positive. So therefore gas to a liquid is negative. Let's go with that one. I haven't got a better explanation in the short period of time that I have to do these multiple choice questions. But that makes sense to me because of this. Going from a liquid to a gas, you have to add energy in, so therefore it's going to be positive. So therefore gas to a liquid, you must get energy out. So therefore it must be negative. Last question that I'm going to do in this round, and then I'll do another video for this stuff. But question 24, the diagram below shows an electroplating cell. Again, you have an object here. That object is going to be the cathode. Let's go with that. What's going to happen is this cell contains liquid of electroplating solution. The electro is run for 1 hour under 3 amps. Which of the following electroplating solution will deposit the largest mass of metal onto an object? All right, so what we mean is we've got the same number of electrons. For all of these, we need to work out which ones the ratio between electrons and mass is going to be the greatest. So this is going to be a toss-up between your charge and your molar mass. Also, you're actually going to toss up between the charge, molar mass, and if the reaction is going to occur. So I think from memory, looking at this, aluminium, a liquid or an aqueous version of aluminium is actually not going to produce anything at all because it's underwater. It's a more reactive metal than water, so it's not going to be that. But our ratio of electrons to metal is going to be a 1-to-1 here, because this is a positive 1, this is positive 2, this is positive 2. So therefore we're going to have, if we have 1 mole of electrons, which we don't, we've got something else, but they're all getting the same amount. So therefore, which one's going to get the most mass? So pretend it's 1 mole. I've got 1 mole of silver, 0.5 moles of cadmium, and 0.5 moles of lead. So let's just work out which one of these is going to produce the most mass. And I go to my periodic table because I don't know these molar masses very well. So silver is here, and it is, whoops, silver is here. So therefore, with 1 mole of silver, I'm going to produce 107.9. So it's 107.9. For cadmium, where's cadmium? This is a bit of a hunt for cadmium. Here it is. Alrighty. And it's going to be, sorry, it's going to be clear, 0.5 times 112.4. It's going to give me 56. So a ratio of that. And lead is, lead's pretty heavy, so it should be down the bottom here. Lead is 207. So lead's 207, it's going to be 0.5 times 207.2, gives me 103.6. So therefore, based on my basic calculations here, silver is going to produce the most mass. What we did here is we just looked at what is the ratio of moles that will be produced, 1 to 2 to 2, and then times that by our molar mass, and we get our ratio of mass produced. And silver had the largest ratio of mass produced. So A is our answer for question, what is it? 24. Done.